Hello folks, we are back with more integration. The last of our integration before we move into the little tidbits at the end of BC. This section is on improper integrals, which we have been kind of leading up to this whole time. Improper integrals really brings a lot of topics that we've talked about already and kind of squishes them into one problem. So they're interesting. There's not a whole lot of In fact, there's no real new techniques in this section. It's just putting the things that we already know together in order to solve some integrals that we wouldn't have been able to solve otherwise. So first thing we want to talk about is what the heck makes an integral improper. A lot of integrals are pretty rude, but it doesn't make them improper. There are really two ways that an integral can be improper. One of those ways is if it has a limit of integration that is infinite. So in other words, something like that, where I'm doing the integral of a graph from 0 out to infinity. Or something like this, where I have a negative infinity up to 5. Or even better, something like that, where we have an infinity at both ends. Okay, so remembering what the area or the integral represents, the area under the curve, if you have a limit of integration that's infinity, then you have an infinitely long area. Okay? Now you might be saying to yourself, well, if it's an infinitely long area, then my answer would be infinity and I'm done. No. Okay. Might be infinity, might not be. So we actually will evaluate these, and sometimes we're going to get a finite answer, if you can believe that. Okay, the other way for an integral to be improper is to have a discontinuity, specifically an infinite discontinuity, somewhere on the interval. And this we've talked about before, and I have said to you many times, you can't integrate over a discontinuity, right? So if you have the function 1 over x, you can integrate from 1 to 7, right? But you can't integrate from 0 to 7 because there's an infinite discontinuity at 0. You can't integrate from like negative 7 to 7 because there's an infinite discontinuity on that interval. So you can't have any infinite discontinuities being involved in any way in an integral. If you do, it's considered improper. So again, if you have something like 1 over x minus 5, at 5, you're going to have an infinite discontinuity. This is a no-no. Okay. Or it could happen like this, where the infinite discontinuity is 3, which is on this interval. Now you may notice by looking at these are a little less obvious than the last kind, right? If you have a limit of integration that's infinity, it usually pops right out at you. These, it's kind of sneaky. It's hiding, right? You don't necessarily, especially ones like these. So one of the things that we have to get trained to do here is when we see a fraction, kind of think, well, where are my infinite discontinuities? Make sure they're not on that interval. Because up until now, you weren't given any integrals that had infinite discontinuities because you wouldn't have known how to handle it. But now we know how to handle it, so it's something that we're going to know how to handle it. So it's something that we have to watch for. Okay, so we'll look at the first situation, the first way for it to be. We'll look at these two situations separately, is what I wanted to say. And then we'll talk about how we're going to deal with them. Now, it also is worth noting that an integral could be improper in more than one way. So if you take a look at this integral, it is improper because it has a negative infinity. It is improper because it has an infinite discontinuity at 5. And it's improper because it has an infinite discontinuity at 3, which is on this interval. So this thing is improper in 3 different ways. And we would need, if we were doing this, to address all 3 of those. And again, the method for which we do it Nothing, not really anything new, but just something, it's kind of a pain, something that we have to do. All right, let's take a look here. Let's talk some terminology before we do anything else. Okay, we know, once again, can't say it enough, that the integral is the area under a curve. Okay, so if I say to you that I want to find this integral, right, the area under x squared between 2 and infinity, so between 2 and infinity, so all of this. You might say to me, Miss Brennan, that is obviously infinity, right? And you would be correct. In this case, this integral comes out to be infinity. And the reason for that is that that function is increasing, right? So if you start thinking about, get a different color here. If you start thinking about an integral in terms of like RAM, right? If I start adding rectangles up here, my rectangles just keep getting bigger and bigger and bigger and bigger and bigger. How is this not going to infinity? It's just going crazy, right? This thing is going to infinity. Compare that to a situation like this. So I have 1 over x squared, and again, I want the integral between 2 and infinity. So I want this area. I want you to see what's happening here. If I start looking at rectangles, if I start looking at RAM rectangles, I want you to notice that my rectangles are getting smaller and smaller and smaller and smaller. And you might say, okay, they're getting smaller, but still, if you add an infinite number of them, it's going to go to infinity, right? And the answer is maybe. If a function is increasing, 100% that thing's going to infinity, the area under it anyway. If it's decreasing though, maybe it is, maybe it isn't. I know that that's a little bit hard to wrap your mind around right now, that it could be anything other than infinite, but it can. And in fact, this integral has a finite value. There is a number, and we will evaluate this integral. The area under this curve between 0 all the way out to infinity is a finite number. Okay. This particular integral then, we say converges. So we have these like vocabulary words. Sometimes they'll say, determine if this integral converges or diverges. Okay. The word converges, and this word's going to come up for us again in chapter 9, super important word, means that it comes to a finite value. That when I evaluate this integral, I don't get infinity for my answer. I get some nice, neat, finite value. Okay. If I don't get a finite value, if I get an infinity or a negative infinity, we say the integral diverges. Okay. So divergence means it goes to infinity or negative infinity. Convergence means that it's approaching some finite value. Now again, it's approaching that value, right? Because we're approaching infinity, because you can't really go to infinity. You keep hearing me say approaching, you know it's coming, right? Okay, so to be super clear on this slide, I just want to say, on the last slide we said if it's increasing, that integral is going to infinity, we're going to say it diverges. If the function's decreasing, it doesn't necessarily mean it's going to converge. We don't know. We have a lot more work to do to figure it out. Okay. If it's decreasing, we've got a chance. There's a chance it's going to converge. Okay. The question is going to be, is it decreasing fast enough? And we're going to find out. Okay. So one more time, these super, super important definitions. If you need to make a pause for the cause to write these two down, please feel free to do so. This is really, really important words here. Really important vocabulary. We say the integral converges if it produces a finite value. So if you go through the process I'm about to show you and you get a finite value, you get a 6 or a 12 or a 1,010,000, that's a finite value. We know that it has a finite area under the curve. It converges. Okay. On the other hand, if you get an infinity or a negative infinity, the area under the curve is infinite, and we say that the integral diverges. You've got to know those two words. They're so super important. Okay. All right. So let's talk theoretically how to solve these, and then we'll put it all together. Okay. This is a little equation I wrote that's not really an equation. And it talks about how we get at improper integrals. So if you have an integral that is improper, what we are going to do is we're going to replace an improper integral with two things. A proper integral and a limit. In other words, what we're going to do is we're going to take an integral that has, say, an infinity in it. And we're going to take the infinity out of there and replace it with a variable. We always use A's and B's and C's for some reason. So then if I do that, so for example, if I take the integral from 2 to infinity and I rewrite it as 2 to b, this isn't improper anymore. Look at me, I took the infinity out. Okay. And then what we do to adjust for the fact that we took an infinity out and replaced it with a b is we go, okay, well, what if I told you that I was going to make b approach infinity? So I took an improper integral and I rewrote it, because I'm being sneaky, as a proper integral that contains a variable. That variable, I just happen to say I'm going to make it approach infinity. So we take an improper integral and we rewrite it as a proper integral with a limit on it. I have times L'Hopital sitting there because the fact is, if you're doing limits involving infinity, it's going to come up. So like I said earlier, this section is like a bunch of stuff, old stuff coming together. So remember limits, remember L'Hopital, and remember integrals, squish, 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 improper integrals. All right, so what we are going to do, again, I already said this, but if you're taking notes, rewrite that integral with a limit to eliminate the improperness of it. So I'm taking an improper integral, I'm turning it into a proper integral with a limit on it. And then once I'm done evaluating the integral, then I'm going to evaluate the limit, which may or may not involve L'Hopital. I have to keep my eye out for that, because anytime you've got infinities kicking around, there's a chance you're going to have L'Hopital. So remember your infinity over infinity, infinity times 0, remember all those good indeterminate forms? Yeah. Infinity minus infinity is a big one here. We get them. If we do, we have to use L'Hopital. Okay, so let's talk about how we do it for reals. All right, this is the first example here. I call this trickery, and you'll see why. All right, so in this example, I have the integral of this fun-looking function from a all the way out to infinity. And a is just a number, right? This is the lower limit of integration. So this is just a constant. It could be a 2, a 3, a 5, whatever. It's just the lower limit of integration. Okay. My upper limit of integration is infinity, and that's where the problem is. So I'm going to take this improper integral and I'm going to rewrite it. I'm going to rewrite it as a proper integral. Now remember, this is still a number. This is the lower limit. Let's note here, this should be a number. But up top here, I'm replacing my infinity with a variable. And notice I'm introducing a new variable. It's not an x or a y. I'm introducing a new variable, right? Sometimes I call this a dummy variable. It's like a placeholder variable, right? I'm just saying, hey, I'm going to put a placeholder in here for some number, and I'll deal with the number later, right? So the first thing we're going to do is actually evaluate the integral. When we evaluate the integral and do upper minus lower, we're going to get an answer in terms of b. Our answer is going to have b in it. Right? And then to turn it back into the thing I originally wanted over there, I'm going to take the limit of that as b approaches infinity. Okay. So think about this. Let me move my heading head again. Originally, I wanted the integral from a all the way out to infinity. That's improper. Can't do it. Okay. So I created this endpoint, this imaginary endpoint. I named it b. I'm going to get an answer here in terms of b. And when I do, I'm going to take the limit as b approaches infinity. In other words, I'm going to take b and I'm going to push it out to infinity and see what happens. Okay? And that's kind of the way we cheat an improper integral. That's why I call it trickery. Right? It's like take the infinity out, replace it with a b, and then when no one's looking, make b approach infinity. So we kind of took the infinity out and then snuck it right back in there. Okay? But I can't integrate with an infinite discontinuity, but I can sure stick it back in there after I'm done integrating. Take that, math. Okay, so that's what happens when you have an infinity at the top end, right? At the upper end of your integral. So again, we leave the lower limit as it is. We replace the top limit with infinity or with a variable. We make it approach infinity. You can imagine that if your improper integral is at the low end, it's very similar, right? So now, instead of my improperness being at the top, it's at the bottom. And this is my upper limit of integration, which should just be a number. So I see my improperness at the bottom there, so I'm going to rewrite it. I'm going to replace my negative infinity, again, with my dummy variable. So this time I'm putting b out here somewhere, right? So I have the area. This integral represents the area between b and a. And then I'm going to take b and push it back to negative infinity, which is where I wanted it to be to start with. So I take I take the integral, I'm going to evaluate the integral, and when I'm done, make b approach negative infinity. Okay, now, okay, I call this one double trickery. In the event that both of the ends are improper, okay. It's actually not too bad. If both of the ends are improper, this is what I say. Pick a number, any number at all, because it's negative infinity to infinity, right? And break this into two integrals. So right now what I have is one integral that's doubly improper. It's improper in two ways. It has a negative infinity at the bottom. It has a positive infinity at the top. This is a no and another no. Okay. So the goal here is to rewrite it into two integrals. So look, whoa, look what I did here. I used that additivity property that we learned a long time ago, that if you want to go from -6 to 6, you could just go -6 to 0 and then 0 to 6 and add them together, right? If I want to go from negative infinity to positive infinity, I'm just going to I broke the interval, this infinitely long interval up at some point c. C could be anything. It could be -100. I use 0 a lot because it's a nice number to work with. It could be it, but it could be any number. You could use 65, whatever you want to use. Now, what's the point of that? Look what I did. I took an integral that had two improper things in it and split it into two integrals that at least individually are only improper in one way. Because now I can actually handle this, right? I can replace this negative infinity with a variable, make it approach negative infinity. I can replace this infinity with a variable and make it approach infinity. It sounds like a lot of work, right? But it's not as bad as you might think because you're only really doing the integral one time. It's just the substituting and evaluating that you have to do multiple times. Okay, so let's do a couple examples. So in these examples, I put all different kinds of integrals so that we can practice integrating. Okay. All right. Okay, so we want to know if this integral right here converges or diverges. So I have the function 1 over x, which we see is decreasing, right? So I can't instantly say anything about it. It's decreasing. Maybe this area between 1 and infinity is finite. Maybe it's not. I have to evaluate the integral and find out. Okay, but I can't instantly integrate this because I've got this problem, right? So let's rewrite it. I'm going to take, instead of 1 to infinity, I'm going to go 1 to b. I don't know why I'm using b. B is for Britain. All right, so I'm going to evaluate this, and then when I'm done, I'm going to take the limit as b approaches infinity. Okay. Again, look what I did. Took the improperness out, replaced it with a variable, just an innocent variable, that later will approach that improperness. Okay. So let's do it. Let's do our integral. So here's my limit sitting out front, waiting to be handled. We'll handle the integral first. Okay, the integral of 1 over x dx is the natural log of x, right? From 1 to b. So I have the limit as b approaches infinity of the ln of b minus the ln of 1. The ln of 1 is just 0. Right? The ln of 1 is saying, what do I have to raise e to get a 1? And the answer is 0. So all I really have here is the limit as b approaches infinity of the natural log of b. And they could have given you this in chapter 2, right? We just have to evaluate this limit. When I evaluate this integral right here, I get that the area under this curve between 1 and b is going to be equal to the ln of b. So all I have to do if I want to evaluate the integral from 1 to infinity then is make b approach infinity. Well, as b approaches infinity, the ln of b also approaches infinity. So the area under that curve is infinite, and I have to say that this integral diverges. So even though it's decreasing, I still get an infinite area if I take this thing all the way out to infinity. All right, let's try another one. Look what we have here. We have, of course, an improper integral that also just happens to be a little partial fraction decomposition. Okay, so first things first, I can't have an improper integral, so let's get rid of it. I'm going to take this infinity and I'm going to replace it. So I'm going to rewrite this integral and instead of 0 to infinity, I'm going to say 0 to b, and then I'm going to go out front and say make b approach infinity. Okay. So we'll look at this as two separate problems. First, we'll go off to the side to evaluate the integral, and then we'll come back and do the limit. Okay, so let's go off to the side and do this integral, shall we? It's been a while since we did a partial fraction decomposition. Okay. Okay, so I've got 1 over x squared plus 4x plus 3. So 1 over x squared plus 4x plus 3. So I have a factorable denominator here of x plus 3, x plus 1. So I'm going to break that into two fractions, a over x plus 3 and b over x plus 1. And then we'll throw it back together again. So I know that 1 has to be equal to a times, x plus 1 plus b times x plus 3. I put it back together again. So this is where we do that thing where we choose x values. You could do a system of equations, or you could be tricky with how you choose your x values. I'm going to choose my x values to be -1 and -3 because that's going to make it easier on me. So if x is -1, then I get, what, a 2b, so I get that b is 1/2. And at x equals -3. This piece goes away, and I get that, I get -2a there, right? So a is -1/2. All right, so I'm rewriting this integral as -1/2. I'm going to take the -1/2 out in front of the, oh no, maybe I'm not going to. So I have -1/2 over x plus 3 plus 1/2 over x plus 1. So if I integrate that from 0 to b, that is going to give me -1/2 ln of x plus 3 plus 1/2 ln of x plus 1. I need more space. So I now need to take my integral and evaluate it, right? I need to put those limits of integration in. So I need to evaluate this from 0 to b. All right, so when I evaluate from 0 to b, plug in my b. So I have -1/2 ln of b plus 3 plus 1/2 ln b plus 1. And then I'm subtracting when I put in a 0, right? So -1/2 ln of 3 plus 1/2 ln of 1. Good news, that's 0. Right. So if you want to, you could do some combining with these natural logs, but you don't have to. So I have 1/2 ln of b plus 3, 1/2 ln of b plus 1, and a plus 1/2 ln of 3 at the end. Right? All right, so just give myself some space again. I have now evaluated my integral. Right? We have done this piece. The integral from 0 to b of that function is that right there. Okay, I'm done with my integral. Now I have to do this part. Okay, so I need to do the limit as b approaches infinity of -1/2 ln b plus 3 plus 1/2 ln b plus 1 plus 1/2 ln of 3. So let us plug in our infinity here. So I have -1/2. This is going to become the ln of infinity plus 1/2, another ln of infinity, plus 1/2 ln of 3. Okay, so if you hope maybe you see what's going on here when you evaluate this limit, I've got -infinity plus infinity. I have a L'Hopital situation here. I have a infinity minus infinity situation, right? This right here. This is infinity minus infinity. You cannot cancel those out. Those are infinities. That's indeterminate form. Okay. Now, before I go for L'Hopital, I'm thinking let's try and do a little algebra rewrite, see if we can avoid it. Right? So what I mean by that is, could I rewrite these in a way using that using the rules of logs? So I'm thinking if I do this, just like flip-flopping the order in which I wrote them. So it's a subtraction, which we know is then a division. So I can say, let me rewrite that as 1/2 the natural log of b plus 1 over b plus 3. And then I still have my plus 1/2 ln of 3. Okay, so the reason that I suggested that is because sometimes if you just do a little algebra rewrite, you can avoid L'Hopital. And if you can avoid L'Hopital, honestly, I would do it. Okay. This problem is complicated enough without bringing L'Hopital into things. So I did my integral, I did my limit, I seem like I have a L'Hopital situation here, but look what I've done. I rewrote this. And we know that when you're doing integrals, limits involving infinity, little things like +1s and +3s, those don't matter, right? Infinity plus 1, infinity plus 3, they're all the same, right? So if we're doing a limit as b approaches infinity, this +1 and this +3, we really don't care anything about. And if we don't care about that, this ends up being b over b, which is 1, right? In other words, as you approach infinity, b plus 1 over b plus 3 is basically just a 1. We learned that way back when we were doing limits, right? And if that's a 1, then the natural log of 1 is 0. Okay? So this whole chunk goes to 0. Okay? And if I evaluate this limit, then all I have left is this 1/2 ln of 3, which is a finite value. Okay. Now, again, you could have gotten the right answer here with absolutely incorrect logic, right? If you had seen this right here and just gone, oh, those cancel out. If it was multiple choice, you'd get away with it, but if it was open-ended, you would not get away with that, right? This is an infinity minus an infinity, so you have to address it, right? You can't just assume it's 0. In this case, though, it turned out to be 0, which is pretty nice. So, I have an integral here that converges. Even though I'm going all the way out to infinity, I have a finite value for my area, which is crazy but true. Okay. And again, look at this function. If I'm thinking about like rectangles here, my rectangles are going to be big at first, but the further I go, the smaller my rectangles become. If you're having trouble thinking about this, I just want to I'm going to give you this one little I guess it's like a little story, before I let you stop listening to me for the day. Sometimes people see improper integrals and they're like, oh yeah, this makes total sense. It was written that an infinitely long area could possibly be anything other than infinity. And other people kind of like want to fight me on this day. And I understand that because it's a little bit crazy to think about. So the example that I always give people is this. Now for this example, my goodness. For this example, you have to believe that I am infinitely thin, okay, which obviously is not an issue, right? Especially since I've been two-dimensional all year for you. Two-dimensional. I am actually infinitely thin to you. Okay, so here's what I want you to imagine. I'm standing at one end of our classroom, and I want to get to the door, right? So let's say that our classroom is, 20 feet across. So 20 feet between me and the door. And I say to you, I'm going to walk over to that door. But I'm mathy. So I'm only ever going to move half the distance between me and the door. So right now I'm 20 feet away. So my first move, I'll cut it in half. I'll go to 10 feet. Right? My second move, I'll cut that in half and go to 5 feet. So now I'm 5 feet away from the door. My third move, I'll cut that in half and go to 2.5 feet. I'm closer, but I'm not there. My next move, I cut that in half and I go to 1.75 feet. Okay. You see what's happening here? I keep taking steps but my steps keep getting smaller and smaller and smaller. And the more steps I take, the smaller they get, because the distance between me and the door is shrinking, but the amount that I move only ever gets cut in half. I'm never going to get to the door. I could take an infinite number of steps. All I ever do is cut the distance between me and that door in half. Now, am I making that distance approach zero? Mm-hmm. But it's not zero. I'm not there, right? I take as the number of steps I take approaches infinity, the distance between me and that door approaches zero. But here's the crazy part. I took an infinite number of steps, but how far did I move? I took an infinite number of steps, but I only moved 20 feet. So even though I took an infinite number of steps, the total distance that I moved was finite. And that's what's happening here. If you think about it in terms of rectangles, as I go out, I'm adding and adding and adding rectangles. But those rectangles are getting smaller and smaller and smaller and smaller. And as long as they're getting small enough, like my steps towards the door are getting small enough, they can still add up to be a finite number. Now, I know that there's a lot of space between a silly analogy about me approaching a door and an improper integral. But hopefully, if you're having trouble wrapping your mind around how an infinite thing can have a finite area, that helps a little bit. This is a very, very abstract concept. And chapter 9 is very similar to this in that abstract way, that we have an infinite number of things adding up to be finite. Okay, so I'm almost afraid to say put any questions you have in the end of the video, but go ahead and put any questions you have in the end of the video. We still have to take a look at the second way an integral can be improper, where you have like an infinite discontinuity in the middle, and we'll do that next time. But I think you've been listening to me quite long enough for now. Okay, have a wonderful day. Again, questions in the end of the video, and we will address tomorrow. Have a wonderful day.